standard model.
Correct.
I guess.
Correct.
Okay.
Right. And the CDM part is cold dark matter. It means there's a lot of dark matter in the universe, but there are other things in that description, like the universe is relatively flat. There's a certain number of neutrinos, particles. It's everything we know. It's an inventory of the universe, but 96% of it is still kind of unknown stuff. In fact, very unknown
96%,
stuff.
that's the dark matter and dark energy combined.
So by the early 2000s, it was recognized, well, we want to understand this more. And so there were folks who were going to measure the radiation left over from the Big Bang, the cosmic microwave background, with a series of satellites, WMAP, Planck, and they were going to very precisely determine the state of the universe as it existed shortly after the Big Bang. The folks who were measuring the cosmic microwave background got a very beautiful baby picture of the universe that has a lot of fine-grained information about the state of the universe. And
excess radiation, for lack of a better term?
But it's a description of what the early soup of the universe looked like. What were baryons, normal matter, how much was dark matter, photons.
A really important snapshot of what was going on. Yeah.
And so the great success was the picture they got of the universe was the same model that we were essentially seeing from these more local observations. There's a lot of dark energy, there's a lot of dark matter, everything fit. Except one thing didn't fit, which is it also predicts how fast the universe should be expanding today. And that number, called the Hubble constant, is something we also can learn by this route that we've been describing, where you measure parallax and you measure stars and you measure supernovae. And using that route, you can measure how fast the universe actually is expanding today. It would be like, having a 2-year-old kid. You measure their height, right? And then you predict how tall they'll become. And then you measure them when they get to that full height. And what if it was off by like a foot or something?
Right.
You'd say,
you'd disown the kid.
Yeah.
You're disappointed.
You're right.
He's still in family therapy.
Yes, I understand. The fact that these two routes from the early or late side of the universe, on the one hand, tell us the same rough, more than rough story.
Basic story.
Yeah, like they're like doppelganger universes, except one is younger and expanding faster, and one is older and expanding more slowly.
That's the 71 and the 67.
The 73 and
73,
67.
You want to explain
Right.
that to
The
folks?
numerical
The
values,
numerical values.
of the Hubble constant.
That's right. And this Hubble tension emerged about 10 years ago.
Tension as in the two numbers are not agreeing.
As in the two numbers are not agreeing.
Now, I have to butt in. I'm in graduate school, and we're fighting over whether the Hubble constant is 50 or 100.
Yeah.
And so you're telling me you're now fighting over whether it's 67 and 72, whatever. And I don't have sympathy for that.
No, but Neil,
my whole time in graduate school, we didn't know the size of the universe by a factor of 2, and you're up to complaining about a few percent.
So now,
Get out of here.
Leave your Nobel Prize.
Let me
melt that down and go to dinner.
Why this is so much more interesting than that was.
Okay, please.
When people were measuring 50 or 100, they were measuring the same thing. They were measuring how fast the universe is expanding here today, often measuring the distance to the same galaxies, the same stars.
When you say here, today, you mean within the Milky Way,
right?
Well,
or just outside the Milky Way,
our region, our
So
part of
what
the universe.
Okay.
So so if I told you the length of this table is such and such, and Neil said no, I get a different answer. The table has one length, right? And so this is something. It's not that profound. One of us is making a mistake. The big difference here is
important point.
We are measuring opposite ends of the universe, and we are using our story of the universe to connect them. And so disagreeing in this case has the potential to teach us something profound about the universe, whereas disagreeing back then just meant people were making mistakes.
And when you say profound about the universe, our understanding of physics and the possibility that there could be new physics out there.
Right. Because how do I go from the early universe to the late universe? I need a function. I need a piece of math to tell me how do I translate from there to there. It's like that kid, they were 2 years old, then they're an adult. How did you guess how tall they would be? Well, you had a growth chart, right?
Yeah.
The growth chart is our model of the universe.
It's a formula.
But, with a growth chart for a kid.
But it's not precise.
Well, you've seen a lot of kids grow up, right? So you have a lot of confidence in the growth chart because they follow that. We only have one universe, and most of it's made of stuff we don't really understand.
Right.
Well, get another universe then.
Well, so
work a little harder.
Right.
Yeah.
So, the fact that they disagree, and Neil makes a good point, it's not a big disagreement in absolute sense, it's like 9%, but our measurements have gotten so precise that it's 5 or 6 times the error bar between them.
I've banned the term error bar because no one knows what the hell that means.
Okay.
The uncertainty.
Sure.
The measurement of the uncertainty of each of those two to quantities does not leave room for overlap.
That's right.
Okay,
So
there you go.
from someone who's not as bright as, well, him, I'm saying, now, could it be that this means that dark energy is shifting? Like,
Yes.
sort of like a petulant
it could be-
teenager, like it's calm and steady, and then all of a sudden, you never understood me, Einstein, and it's slamming the door on you, right? Like, is it that possibility? Is that happening?
Yes. I would say that we may be discovering that what we call dark energy is a general phenomenon that happens all the time in the history of the universe. So let me tell you this. We invoke dark energy shortly after the Big Bang in a period called inflation to inflate the universe, okay? We give it the name inflation, but it's dark energy, okay? We have the universe currently accelerating now. That's dark energy.
By the way, it was called inflation because the idea was advanced in the 1970s when we had like 18% inflation. So the word had a lot of currency.
I didn't know that. Is that right?
Yes, it was under President Carter, and inflation was like 20% inflation.
The win button, whip inflation now. Remember that win button?
We have something in physics that's an important part of physics called the Higgs field, which is a field in space that gives rise to mass for particles. That is an invisible energy in space. So this is a regular feature now in physics, is to recognize that there are invisible energy fields. And in Einstein's theory of gravity, an invisible energy field plus Einstein's theory of gravity automatically has this consequence of giving a push to the universe. Ooh. And so I would say at this point, we are sort of watching the universe to sort of try to learn when episodes like this may occur. Maybe there's only 2, maybe there's 10.
Is that there's, from my understanding, there's 5 possible reasons for this Hubble tension. Is that the new dark energy theory? Or is that the early
so there's an
energy?
early dark energy theory which posits a 3rd episode of dark energy. Not inflation, that was the beginning, not the current one. So
is that the turbo boost one, or is it something different?
I don't know about the turbo boost, but it goes by the name early dark energy. But it's the same concept, is that, if you give a kick somewhere along the way, then using the simple form of the cosmological model to connect 2 endpoints, you're not going to quite get things right.
Doesn't it have to be motivated to manifest itself? And so what would manifest a pulse of dark energy in a place unexpected?
Right. It usually ties to a particle, and it usually ties to some event, some symmetry breaking or something like that. And it becomes very theoretical. I mean, theorists argue that sounds reasonable. That doesn't sound reasonable. To me, they all sound kind of like la, 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 la. But, I look at it like, all right, how many times have you invoked the tooth fairy in this conversation? And, I've learned that like a close cousin of the tooth fairy is not a new invocation of the tooth fairy. It's just her cousin. And so to me, there's a big tooth fairy that we've already been living with for a long time.
Sure.
And these are like revisits of the tooth fairy.
All right, so
I'm an observer, so this is not, I look at stuff.
Is there a way to reconcile this without having to invoke another tooth fairy?
Yes.
You invoke Santa Claus.
Exactly.
Well, first of all,
big fan.
There are a lot of ideas.
He leaves better gifts.
Yeah. One way to play the game is to change the way the universe looked before this radiation from the Big Bang leaks out. So
how do you change the way it looks?
So change our understanding.
Yeah, our understanding.
We're not changing it. What do you think we're God?
So it's a kind of a plasma soup. And so even something as subtle as saying if there was a magnetic field in it, that could start this process of collapsing by gravity.
Or there could be new particles.
There could be a new particle. That is absolutely another possibility. Right? It rearranges the way energy is distributed in the early universe. And so there are many ideas. Electron, mass decaying, interactions between dark matter. See, when physicists start out with the cosmic microwave background, they have to build a model of what's going on in the universe. So this would be like some new attribute going on there, or it could be something late in the universe. Like as dark energy emerges, it's not this cosmological constant, which means static, uniform, unchanging, but it has some kind of mind of its own.
Right, so you have your option to either make the early universe match the current universe, or the current universe match the other, or have them do something both that can meet in the middle.
That's exactly right.
Okay, so how uncertain are the nearby measurements? Seems to me those should be pretty secure.
Yeah, so I would say now after 10 years of scrutiny, they're pretty darn good. What I can tell you is, having made a lot of those measurements with the Hubble Space Telescope, along came the James Webb Space Telescope, and it was like, I don't know, it was like riding the your first little bike when you were a kid, and then like somebody gives you a 10 speed, and you're like, oh my god, and you're like doing laps around what you did. So I've been doing laps around the work that I've been doing over the last few years, and the images are pristine, the measurements are textbook, but the answer is the same. And so the fact that James Webb is confirming what Hubble is confirming that this is a real problem.
And that deserves, I got to emphasize this, because what he just said is you can make measurements with whatever precision your equipment allows.
Right.
And then you extract from that an answer in the din of cosmic noise. It's kind of saying this. If you have better data and you get the same answer, you're good.
Right. That's right. And the signal to noise is 10 times higher for the measurement I'm making with James Webb than it was for Hubble. So if you get a full order of magnitude improvement and nothing changes, that's very compelling.
So for those at home, and in simplified terms, there was a debate. Well, maybe the math or the way we're doing the math is off, and then the Webb telescope enters the picture and tells you maybe not. So now you have to go to the idea that maybe there's something about the world of cosmology that we're not understanding, or there's something new, or there's new physics.
I'm going to say, or some subtlety, something being lost in translation between the universe we see and how we transform it to these sort of mathematical models. Like this is the sky, and the telescopes confirm that is the way the sky looks, but perhaps there's some subtlety in the way we translate that into math, or we translate to the beginning of time.
Let me go back 130 years.
Yes.
I think
that's you living in the past. Go ahead. When I was a kid.
Go back then.
Yeah, let's go back.
We were riding high on classical physics.
Yes.
And people said, look, there's not much left to discover in the universe.
Right.
We got this. We got Newton.
Right. It's all done.
We got thermodynamics.
Right.
We got this. And there are just a few clouds on the horizon.
Yeah.
That
the precession of Mercury isn't quite working out.
Yeah,
right.
but we'll solve that soon.
It's just another planet out there.
So
probably.
don't go into physics because it's about to end. Bada bing. Quantum physics comes up, and special relativity and general relativity and all that came with that.
Right.
Is there something lurking?
Right.
In the dark, in the woods, that will need a much bigger transformation of our understanding than just meddling in here and there.
Right. The answer is I don't know, but what
That's
I do.
a good answer. Good scientist.
But I do know the
I was
process.
hoping for an answer. I got to be honest with you.
I do know the process.
I don't want to die soon.
Here's the process. We're very happy with the model, the science we have. We go out and we predict experiments and we do things. And then you start to build up these cracks or tensions, little funny things. The precession of Mercury is not following Newton's theory. There's supposed to be an ether out there, and we're supposed to be traveling through it. So the speed